Hello, analysts. So, what I'd like to do today is to start in on an entirely new topic. So, we've done lots of things with sequences of numbers and their limits. There's another thing that you'll remember from calculus as being pretty important, the notion of the limit of a function. So, let's recall that definition. This is where we'll begin. Let U be a subset of R. Let f from U to R be a function. Let P and L be an R. Then I say that the limit as x approaches P of f of x is equal to L if, and you know exactly what I'm about to write. You'll remember it from calculus 1. If for all epsilon bigger than 0, there is some delta bigger than 0, so that for all x in U, if 0 is less than the absolute value of x minus p, the place where I'm taking the limit, this p is the same as this p, is less than delta, then absolute value of f of x minus the alleged limit is less than epsilon. So maybe just for the sake of comparison, let's write down that in shorthand and also the definition of the limit of a sequence. So x sub n goes to a number L means for all epsilon bigger than 0, there exists a big N such that for all little n bigger than big N, yeah, this is fine. And I say that f of x, I'll use the word limit. I say that if for every epsilon bigger than 0, there exists a delta bigger than 0 such that for all x in U, if 0 is less than absolute value of x minus p is less than delta, then absolute value of f of x minus L is less than epsilon. So there are some immediate comparisons. You start with the declaration of an arbitrarily small epsilon, and the end goal is the object in question is within that epsilon of the alleged limit. The definition of the limit of a sequence says there exists some threshold number big N, so that as long as little n is bigger than big N, the limit of a function says there's some threshold positive number delta, so that as soon as x is that close to p but not equal to p, then you get this proximity result. So these really are very similar definitions. They're capturing something really similar. The only difference is for a sequence, I think about the parameter big N, little n getting big. For a function, I think about the input x getting close to p instead. Cool. All right, so that means that a lot of proofs are going to look really similar to proofs you already know how to do. Let's prove that the limit of 2 minus 4x as x approaches 3 is the thing that you think it is. And take a moment, look back in your Calc 1 brain. What do you think this should be? Well, there's this philosophy that, like, if you have a reasonable function, a continuous function, you should be able to just plug in 3. Or you say, well, that should be like 2 minus 4 times 3. Gosh, that's 2 minus 12 is negative 10. There's what I think the limit should be. Let's try to prove that. So I'll let the statement of the limit guide the proof. I need to prove something is true for every epsilon bigger than 0. So I should start with something like consider any epsilon bigger than 0. Next, there exists some delta bigger than 0. So I need to come up with a choice of delta. I will let delta be a thing that I get to choose. With that choice of delta in mind, I now get to consider any x in U. I now need to show if this is true, then that is true. How do you show an if then? You assume the hypothesis. I now need to show the conclusion. So I'll try to write down an absolute value of f of x minus L is. I'll just try to do some manipulation to it. Then, well, what is the function in this case? It is 2 minus 4x minus L. And now I guess I just have to do stuff to it. This is something given by a formula, so let's just try to simplify it. All right, so that is the absolute value. Gosh, double negative becomes positive. 2 plus 10 is 12. Minus 4x plus 12. Do some stuff to that, and in particular, oh, that p shouldn't be a p. Where am I taking the limit? I'm taking the limit as x approaches 3. All right, so let's manipulate this. So maybe I'll do this to that expression. That's absolute value of negative 4 times x minus 3. All right, that factorization is true. Oh, but this is a constant times a thing in an absolute value. I can pull the constant out at a cost of making it positive. X minus 3 in absolute value is less than delta. And now you know the standard game. I've got something here that I can set equal to epsilon and solve to see what delta is. It looks like that'll do. So let's just see if this proof actually works. We'll consider any epsilon bigger than 0. Let delta be that. Let x be in u. Assume this. Then the thing I want to be small is equal to minus 4x plus 12, is equal to this, is equal to that, is less than 4 times delta. 4 times delta is epsilon by our choice of epsilon. So writing that down, thus, for all epsilon bigger than 0, there exists a delta bigger than 0, such that for all x in, what's the domain here? The domain is the real numbers. Oh, that was a mistake. You don't just always write u, you write what the domain actually is. Thus, such that for all x in R, if absolute 0 is less than the absolute value of x minus 3 is less than delta, then absolute value of 2 minus 4x minus 10 in absolute value is less than epsilon. So the limit as x approaches 3 of 2 minus 4x is equal to negative 10. There you go. So there are some things to absorb about the definition of the limit. Namely, let's look at this bit. This bit. So there's a universal quantifier followed by an if then. So what's something that's worth noting about if thens? If the hypothesis is just always false, then the whole if then is automatically true. So if you happen to look at a p-value for which there are no x values here, then it doesn't matter what you put here, you'll satisfy the definition of the limit. So that's like a weird thing. So it's, I mean, this isn't going to be a terribly informative sentence. If there is no x in u with 0 is less than the absolute value of x minus p is less than L, then limit as x approaches p of f of x equals L is true no matter your choice for L. And that's really weird, right? So in order to avoid that weirdness, we'll just not ever try to take a limit in that situation. For a subset U in R and a point P in R, that point P is called an accumulation point or limit point. I'll more often use limit point than accumulation point. I think the textbook uses accumulation point though. If for all delta bigger than 0, there exists an x in U with zero less than the absolute value of x minus p is less than delta. So what's like the picture of that? There's the real line. There's the point P. There's a little delta neighborhood. There must be stuff in the set, in that orange interval, other than the point P. That's what it means to be a limit point. A point P which is not a limit point is called an isolated point, if it's also in U. So let's quantify that. So a point is isolated if the negation of this is true. So let's negate that. You negate a universal, you see that there exists a delta bigger than 0, such that no matter what x you choose in U, this is false. So what is this? This is like two inequalities that must be true. This inequality and that inequality, you negate an and, you get an or. And I'll rephrase that again in a second. That's right. This obviously simplifies. So this says that there exists a positive number delta such that no matter what x you pick in U, either, let's take a look at this. That just means x is equal to p, right? X minus p in absolute value can't be negative, so it must be equal to 0 if that is true. Or it's kind of far away. So phrasing this again, an equivalent definition. There exists a delta bigger than 0 such that the only x in U with absolute value of x minus p is less than delta is x equal to p. That seem pretty okay? Like, asking doesn't do any good. Cool. So there's a definition of an isolated point. The idea is, there's the number line again. There's p. There's this delta neighborhood. So a point is isolated if this itself is the only point in U with that. So all of these points cannot be in U. And hence isolated. It does that this point P is in U, but it doesn't have any neighbors that are also in U. So the other thing that you'll remember from your days in Calc 1 is the definition of continuity. What does it mean to be continuous? Let U be a subset of R and F from U to R be a function. Let P be in U. We say that F is continuous at P if And you know exactly what I'm about to write. For every epsilon bigger than 0, there exists a delta bigger than 0, such that for all x in U, if absolute value of x minus p is less than delta, then and right, that's exactly the definition you remember. And maybe you remember it informally as saying that when x is close to p, then f of x is close to f of p. But exactly how close? Well, that's how close. So there's going to be 2 lines right here. So I'll just say a function is continuous on a whole set if for all p in U, f is continuous at p. Or expanding that a little bit, for all p in U, this has to happen. For every p in U, for every epsilon bigger than 0, there exists a delta bigger than 0, such that for all x in U, if the absolute value of x minus p is less than delta, then the absolute value of f of x minus f of p is less than epsilon. So maybe I'll point this out. If you are trying to prove something is continuous, you would start with consider any p in U. Then you would say consider any epsilon bigger than 0. Then you would say let delta equal something. And this something would be allowed to depend on the point p you choose and the positive number epsilon. Cool. So let's come up with a proof. Let's prove that 3x minus 2 is continuous at x equals 1. And let's see, I can zoom out that far. Now you can see the definition. So let's try to prove the sucker is continuous. So I've already picked the input. I guess that should be p if I'm using the same variable name as above. Let's do it. So let's let epsilon be bigger than 0. Let's let delta be a thing that I get to pick. It can depend on epsilon, and it can depend on the fact that I'm choosing this point p equals 1. Well, what does that even mean? If I picked a different point, I could have a different delta. Let delta be whatever I'm going to choose. I'll now consider any x in the domain. The domain right here is the whole of the real line. I'll assume absolute value of x minus p is less than delta. I now need to show this. So let's do that. Then absolute value of the function 3x minus 2 minus f of p, and p is 1, 3 times 1 minus 2 equals, so I guess now like simplification has to happen. 3x, let's see, minus 2, this whole thing is minus 1, but then it's plus 1. No, it's 1, and then it gets subtracted. Whew. Negative 2 minus 1. Is equal to 3 times the absolute value of x minus 1. But I got to assume that the absolute value of x minus 1 is less than delta. That's less than 3 times delta. Oh, but this is like the standard game. And I want that to be equal to epsilon. So let's just set that equal to epsilon. It's easy enough to solve. Let delta be epsilon over 3. Groovy. And now just a concluding sentence. Thus, for all epsilon bigger than 0, there exists a delta bigger than 0, such that for all x in the real line, if the absolute value of x minus 1 is less than delta, then absolute value of f of, well, I haven't called the function f. No, I did call the function f. F of x minus f of 1 is less than epsilon. This function f is continuous at 1. Groovy. So the next thing I want to do is a comparison between limits and continuity, and it'll be something that you'll find quite satisfying, because maybe you remember, depending on the philosophy that you took when you had Calc 1, continuity doesn't have its own like epsilon delta definition. Instead, maybe you wrote something down that has like just a definition in terms of limits. You say a thing is continuous if some limit statement happens. That's what my goal is going to be. So let's just set it up. So given a function, I can talk about the limit of that function at any limit point of its domain. I can ask about limits at limit points of the domain. Given a function, I can ask about continuity of that function at any point in U. And all right, those don't need to be the same, right? If your U is, for example, I don't know, 0, 1, then 0 is a limit point, but it's not in U. Let's suppose it was that together with the singleton 2. Then 2 would be in U, but not a limit point. So maybe you have points that are both in U and limit points. Those would be like these points. And as long as you have points that are both in U and limit points, then theorem 7.1.5, let U be a subset of R, and f from U to R be a function. Let P be a limit point of U. Then the function f is continuous at P if and only if the limit is as x approaches P of f of x is equal to f of P. Nice. So let's give the proof. Let U be a subset of R, f from U to R be a function, P be a point in U, and P be a limit point in U. Right, those are the assumptions. U is a set, f is a function defined on U, P is in U, and P is a limit point of U. Let's suppose, to do one of the directions, that the function is continuous. I need to prove this. So let's do a quick aside. Just think about what it is that we're going to try, what we need to prove. So what is it that we want to show? We want to show that for every epsilon bigger than 0, there exists a delta bigger than 0, such that for all x in U, if 0 is less than the absolute value of x minus p is less than delta, then absolute value of f of x minus the alleged limit, so this is the thing that is taking the job of L, is less than epsilon. So to set that up, I should start by considering any epsilon bigger than 0. Next thing I do is I need to come up with a positive number delta. I'll use continuity to do that. Since f is continuous at P, by assumption, we see that there is some delta greater than 0. So I've considered any epsilon, and I'm now coming up with my choice of delta, such that for all x in U, and now I'm using the definition of continuity, if absolute value of x minus p is less than delta, then absolute value of f of x minus f of p is less than epsilon. This right here is just by the definition of limit. No definition of continuity. Nice. All right, so I've just come up with my positive number delta. Now I need to consider any x in u, check, and I get to assume this. All right. I need to conclude this. Well, there's a fairly straightforward thing to do. Well, since I know this, that's like two inequalities must be true. I definitely also know that. So in particular, we have absolute value of x minus p is less than delta. But look at this if then. Since the absolute value of x minus p is less than delta, then absolute value of f of x minus f of p is less than epsilon. Thus, we may use the continuity of f, this line, to conclude absolute value of f of x minus f of p is less than epsilon. So let's just summarize. We considered any epsilon bigger than 0, hopefully. Yes. We came up with a trace of delta. We considered any x in u. We assume 0 is less than the absolute value of x minus p is less than delta. We showed f of x minus f of p is less than epsilon. So that means that. So that completes half of the proof. Let's go the other way. It will be mildly harder. So let's write down the thing that we want to show. So we want to show for all epsilon bigger than 0, there exists a delta bigger than 0, such that for all x in u, if absolute value of x minus p is less than delta, then absolute value of f of x minus f of p is less than epsilon. And, well, right, I want to assume limit equality get continuity. So I start by assuming limit as x approaches p of f of x is equal to f of p. I'll consider any epsilon bigger than 0, because the thing I want to show is something for every epsilon bigger than 0. Next, I need to come up with a delta bigger than 0. Well, this gives me a trace of delta bigger than 0. Since limit as x approaches p of f of x is equal to f of p, we get that there exists a delta bigger than 0, such that for all x in u, if 0 is less than absolute value of x minus p is less than delta, then absolute value of f of x minus f of p is less than epsilon. All right, so now I've considered any delta big, I've come up with my choice of delta. I now consider any x in u, and I get to make an assumption. I get to assume that the absolute value of x minus p is less than delta. I need to show this. And well, if I knew this, then I would get that automatically, right? That's how if-then statements walk. If you know the hypothesis, then you know the conclusion. But I don't, right? I don't know that 0 is less than the absolute value of x minus p. Well, so let's just break it up into cases. Either 0 is less than the absolute value of x minus p is less than delta, or 0 is equal to the absolute value of x minus p. All right. In the first case, we see that, well, I don't know, maybe we'll label this really quickly with a star. By star, since 0 is less than the absolute value of x minus p is less than delta, we conclude this. Which is exactly what we need. So now I just need to deal with this case. So let's look at case 2. What's the only way an absolute value can be 0? Well, the only way an absolute value can be 0 is if the thing inside is 0. The only way x minus p can be 0 is if x is equal to p. In the second case, that absolute value of x minus p equals 0, we get x equals p. And that's really strong. So let's just see if that's good enough to get this result. Then absolute value of f of x minus f of p, well, x is p, so that's absolute value of f of x, f of p is x, minus f of p. Oh, that's 0, which is in particular less than epsilon. Nice. So in either case, we got this conclusion. So what have we shown? We've shown that for any epsilon bigger than 0, there is a delta such that for all x in u, if absolute value of x minus p is less than delta, then absolute value of f of x minus f of p is less than epsilon. That means that the function f is continuous. Cool. So unfortunately, I started this and I didn't actually make note of what my start time is. And I don't think that this device gives me a sense of how long I've been going. So I'm going to go through this lecture. Might go on a little bit long, or it might be short. I have no sense. So let's carry on. So the previous thing says that if you look at a limit point that's also a point in U, then continuity is detected by limits. At non-limit points, at isolated points, the concept of taking the limit totally explodes. The limit as x approaches p of f of x is equal to everything, which isn't a behavior you want. Let's see what continuity does at isolated points. And in fact, it also does something pretty dumb. So let's let U be a subset of R and f from U to R be continuous. Let's suppose that P is isolated. Then, no matter what the function f is, it is continuous at P. So this might seem like really strong and exciting, but it's actually kind of upsetting. A thing that's always true is like you don't get any information out of it. So continuity is, meaningless is probably a pretty good word. It's a thing that's always true at isolated points. So let's prove the proposition. So I need to show that this function is continuous. So I need to consider any epsilon bigger than 0, come up with a choice of delta. Well, the only hypothesis I have is that P is isolated. Since P is isolated, we have that there exists a delta bigger than 0, such that for all x in U, either absolute value of x minus p is bigger than or equal to delta, or x equals p. All right, so there's my choice of delta. Let's see if that's a good enough choice of delta. So let's consider any x in U. So suppose that x is in U, and assume that the absolute value of x minus p is less than delta. Oh, so let's absorb this. So let's look at that line. If I know that the absolute value of x minus p is less than delta, then that's definitely not true. But there's an or statement that I know is true. I know that either this is true or that is true. This can't be true, so that must be true. So we've just seen that that means, well, maybe I should write it out in more detail. Since not absolute value of x minus p is less than delta, it must be that x is equal to p. All right, so x is equal to p, but then absolute value of f of x minus f of p is equal to the absolute value of f of p minus f of p, since x is equal to p. That is equal to 0. 0 is less than epsilon because epsilon is a positive number. Thus, we have found that for every epsilon bigger than 0, there exists a delta bigger than 0, which let's just go ahead and notice that did not depend on the choice of epsilon. That just depended on the fact that this sucker was isolated, such that for all x in u, if the absolute value of x minus p is less than delta, then absolute value of f of x minus f of p is less than epsilon. So f is continuous at p. Groovy. So the last thing that I want to do is not prove the limit laws for limits of functions. We'll do that next time using the philosophy of sequences. I want to state them though. So here's a list of results. Go through them and complete them. You already know what's going to go in there, so just do it. Maybe pause me, and then come back. So you've come back now. If f of x equals c as a constant function, then the limit of that constant function is c. If a function is always equal to c, then as x approaches p, that constant function gets close to c. If f of x equal to x is the identity function, then the limit as x approaches p of that function is p. Maybe I should add another line there. What does this really say? This says the limit as x approaches p of x is equal to p. As x gets close to p, x gets close to p. If f of x gets close to L and g of x gets close to m, then f of x plus g of x gets close to L plus m. Same thing with subtraction. Same thing with multiplication. And maybe I'll give a quick advertisement. I've sketched an argument for this as a challenge problem for you to go through. Go and read through that challenge problem, write it up, and then come show me. If f gets close to L and g gets close to m, and you never divide by 0, and you never divide by 0 in the limit, then the limit as x approaches p of f of x over g of x is L divided by m. And we've already proven those things for sequences. You can come up with proofs for limits of functions, which are basically the same as the proof for sequences. So I'm not going to try to prove them using such a strategy. Next time I'll prove them by building a new tool for how to think about limits of functions in terms of sequences. For now, all I'll do is give some corollaries regarding continuity. So let's look at what each of these says. So this says that if you have the function that's always equal to c, then the limit as x approaches p of f of x is equal to c. Oh, but notice this c, that's the same thing as f of p, right? Because this function is always equal to c. So that means this function is continuous. Similarly, the identity function is continuous. Oh, the scalar multiplication rule didn't show up here. That's okay. It is for continuity here. If you have a continuous function, then c times f is continuous. If you sum two continuous functions, you get a continuous function. If you subtract two continuous functions, you get a continuous function. If you multiply continuous functions, you get a continuous functions. If you divide continuous functions and are very careful to not divide by 0, then you get a continuous function. And all of these proofs have the exact same claim. So I'll do the one which maybe seems like it should be the most difficult right here, and then you can port over that argument to any of the other ones. So let's do it. So let's suppose that u is a subset of R, p is a point in u, f and g are continuous functions at p, and g of x is not equal to 0 for all x in u. I want to show that f of divided by g is continuous at every x. All right, so there are like two cases. At p. There. Either p is an isolated point or p is a non-isolated point. If p is an isolated point, then proposition 7.1.6, I'll flash it back to it to just to remind you what it says. It says if f is a function defined on u and p is an isolated point of view, then f is continuous at p. Every function is continuous at isolated points. By proposition 7.1.6, we see that every function is continuous at isolated points. So since P itself is an isolated point, so f over G is continuous at P. On the other hand, if P is a limit point, well, then P is a point in U, which is also a limit point of U. So theorem 7.1.5 reveals something. I'll scroll up and remind you what that is. 7.1.5, let U be a subset, F from U to R, let P be a point in U that is also a limit point. Then a function is continuous if and only if a limit thing happens. And that's an if and only if, so we can go back and forth using it. So using that, I know that f and g are both continuous, so that means f of p is equal to the limit giving myself space for the x converges, x goes to p. And g of p is equal to the limit as x approaches p of g of x. Now I'm going to appeal to theorem 7.1.7, and it's claim 7, but I'm going to check if that's actually correct. Theorem 7.1.7, claim 6. Oh, one of the items must have been deleted. That's weird. Says that if f of x converges to L and g of x converges to M, and you never divide by 0, then f of x over g of x converges to L over M. So by theorem 7.1.7, claim 6, we conclude that limit x converges to P, f of x divided by g of x is equal to the limit of f of x. And notice I'm not putting the x goes to P just to save myself space. There's only one place I'm taking the limit in this theorem, so I don't lose any information. Combining that with the line above, this is equal to f of p. Limit as x approaches p of g of x is equal to g of p. So in particular, this function has the property that when you take the limit as x approaches p of this quotient function, you get the same thing as plugging in x equals p. By theorem 7.1.5, remind you what that is again. If a function has the property that when you take the limit as x approaches p, you get the same thing as f of p, then that function is continuous at p. Since limit x approaches p, f of x over g of x is equal to f of p over g of p, we conclude that f over g is continuous at p. All right, so we considered any point in the domain, I hope, with the functions being continuous at p and the function g of x not equal to 0. I concluded that f over g is continuous at p. That's exactly what I needed to do. For claim 6 will be a very similar proof. So maybe I'll leave that to you. I'll give you the comment that that 6 there should probably be a 5, I think. And if you want to do something with multiplication, you should use the thing that uses multiplication. All right, nice. So I'll stop here. Thank you for watching. I'll see you in class, in person, on Monday. Feel free to shoot me emails over the weekend. I'll do my best to be reasonably responsive. Ciao.